All right, welcome to part 4 of the Stats Methods video lecture series here. And so we were just looking at the results for the mean scores, the mean noise blast scores for those in the Karate Kid 3 condition versus those who watched Gorillas in the Mist. And so these mean scores, again, we're seeing a mean slightly over 4.5 in Karate for those who watch Karate Kid 3 versus a mean a little bit under 4 in Gorillas in the Mist. And so these mean scores, I should mention, are descriptive statistics. So descriptive statistics organize and summarize data at sort of the first stage of trying to get a sense of what's going on in the data. So the mean score of 4.6 here versus 3.9, those are descriptive statistics. They are describing what's seemingly happening in these conditions. And so just based upon these mean scores, we're finding a difference of around 0.5. It looks like those who watch Karate Kid 3 were actually set a higher noise blast than those who watched Gorillas in the Mist. But as I said before, just because we observe or find a mean difference does not mean this difference is real or important. All right, doesn't mean that the difference is real or important. So let me try to explain why we can't assume that just because we observe a difference doesn't mean the difference is real or important. So the next step, after we calculate the mean scores for each condition, is actually looking at some inferential statistics. And so specifically, we are going to focus our attention to p-values. So when we start taking a look, especially at journal articles, we're going to see p-values. And so p-value is an inferential statistic that helps us decide whether any difference is real or true. All right. So let's say, for the sake of argument, this picture represents the entire population that we're interested in here. So, Bushmen in the Karate Kid Gorillas in the Mist experiment here, got college students. So let's say that we're just trying to generalize these results to college students. So let's say this picture represents, all college students. So let's say this picture represents all college students. And of course, this picture does not actually illustrate all college students, but there's a shit ton of people in this picture. It works. So let's just pretend, for the sake of argument, that this photograph represents our entire population, all college students. Right? Now, for any given study or experiment, we usually don't get everyone in the population, right? We'd like to. It'd be amazing if we could get every single person in our population to participate in our study experiment, but usually it's just not feasible. It's just, if we try to run a study or experiment with all college students, we can't do it logistically, right? So we rely on, we don't get everyone in the population. So, right, we get a select group of people from this population, which is called a sample. As you probably already know, right? And so, Bushman got his sample of 299 college students, from the university that he worked at, right? And he found a difference of a 0.5 between the Karate Kid 3 condition and the Gorillas in the Mist condition. So the question is, this difference that we're finding, that Bushman found, right? Would this difference replicate if we got everyone in the population? Right? How do we know that difference that we're finding, that 0.5 difference that we're finding between the Karate Kid 3 condition and the Gorillas in the Mist condition, how do we know that we're going to replicate that 0.5 difference if we got everyone in the population? Of course, right, research is a programmatic, right, collection of data. It's a logical sequence of studies, right? So we could get more samples, right? We could change the manipulation, have students watch different movies or play violent video games versus non-violent video games, right? So we're going to do a logical sequence of studies where we're going to get, right, different samples, try different manipulations out, right? But even if we did the same study that Bushman did with different samples, with any given sample, how do we know that the difference that we're finding actually represents the entire population? And the simple answer is that we don't. We'll never be 100% sure that whatever difference that we're getting with our sample actually reflects everyone in the population, because we didn't get everyone in the population. So any result that we get with our sample will never be 100% confident that whatever difference that we're finding, whatever result that we're finding with our sample actually would replicate if we got everyone in the population, because we don't have everyone in the population. So this is where inferential statistics and statistical significance comes into play. So our p-values will tell us whether we have a statistically significant difference. All right, so if we have a statistically significant difference, this means we're at least 95% confident that the mean difference is greater than 0. So technically, this is what the p-value is going to tell us. How confident are we that the mean difference that we're finding is far enough away from 0 to indicate a true and real difference? In Bushman's study, right, we saw a difference of about 0.5. So is that 0.5 big enough, far away enough away from 0 to suggest a true and real difference? Right. Because a mean difference of 0, right, if we had a difference of 0 between the two conditions, right, that would indicate that the manipulation didn't have any effect, right, on noise blast intensity. Well, we got a difference of 0.5, right? So is that 0.5 far enough away from 0 to indicate that this is a true and real difference? And so this is what p-values tell us, right? And so p-values tell us, again, how confident we are that the mean difference here is far enough away from 0 that the difference is actually real, it's true. So p-values range from approximately 0 to 1. So I say approximately 0 because p-values can never truly equal 0. And I think that'll make more sense as we sort of go through how we interpret p-values. But p-values range from approximately 0 to 1. So it's a very standardized range here, 0 to 1. So let's say that we got a p-value equal to 0.3. So let's say we got a p-value equal to 0.3. What does that actually mean? So we've got a p-value of 0.3, how confident are we that the mean difference is big enough that the difference is actually real or true? And so you probably have two guesses at this point. So if you get a p-value of 0.3, you're probably either thinking, oh, does that mean that the sort of most obvious answer here is that if we get a p-value equal to 0.3, that would mean we have that we're only 30% confident that the mean difference is far enough away from 0 to suggest a true and real difference. But actually, p-values actually work in sort of the opposite way that you think they would, right? So p-value equal to 0.3 actually means that we are 70% confident, not 30%. Right? So as p-values get bigger, we are less confident. Or you can say that as p-values get smaller, we are more confident. Right. So to actually figure out the percentage confidence here, we do 1 minus our p-value times 100. So 1 minus 0.3 gives us 0.7. 0.7 times 100 gives us 70%. Right. So then if we got a p-value of 0.4, right, a p-value of 0.4 would mean that we are 60% confident, while a p-value of 0.2 would mean that we are 80% confident. So if you think about that, statistical significance means that we're at least 95% confident, right? So what p-value is equivalent to 90% confidence, right? So if 0.3 is 70%, 0.2 would be 80, 0.1 would be 90, and then p equal to 0.05 would be 95% confident. All right. So p-values less than or equal to 0.05 are statistically significant. P-values less than or equal to 0.05 are statistically significant. All right. It's one of those things that you get out of Psych 200, you get out of stats class, and it's one of those things that hopefully stays with you here. P-values less than or equal to 0.05 are statistically significant. Meaning, again, we're at least 95% confident that whatever mean difference that we're getting here is greater than 0. So what's the p-value for Bishman's study, right? What's the p-value for the difference that we're finding between those who watched Karate Kid 3 versus those who watched Gorillas in the Mist? P-value is actually 0.002. The p-value is actually 0.002. So you have to think about, right, p-values less than or equal to 0.05 are significant. Is 0.002 less than 0.05? Yes, it is. So we do have a significant difference here. We actually have a significant difference. So we're actually quite sure here, right, because if we do 1 minus 0.002, right, times 100, right, we are 99.8% sure that this difference of approximately 0.5 is bigger, far enough away from 0 to suggest a true and real difference here. If we think back, right, to our definition of a true experiment, right, we have a manipulated IV and random assignment, right? And so if participants were randomly assigned to these different conditions, the manipulation must have caused the difference in noise blast intensity, right? So if participants' experience in these different conditions were exactly the same, right, except for the 15-minute movie they watched, this difference of 0.5 must be due to the movie they watched, right? So it seems like Karate Kid 3 seemingly increased the intensity of the noise blast significantly, right? Because we have a significant difference here, right? So Karate Kid 3 significantly increased noise blast intensity compared to those in the Gorillas in the Mist condition. So as long as participants were randomly assigned, this difference that we're finding here, the significant difference, must be due to the movie they watched. Because random assignment also helps make the conditions equivalent here. Because one critique that a lot of undergraduates, think about is, well, what if you have maybe more people that are prone to physical aggression in the Karate Kid 3 condition? Like, what if we had more men in the Karate Kid 3 condition, right? Because there tends to be a big gender difference in usually physical aggression, with men tending to be more physically violent than women. And so as long as we randomly assign people to conditions, we should have like equivalent levels of men and women in each of these conditions, right? So if we use random assignment, we should get, again, equivalent numbers of men and women in each of these conditions. So random assignments helps equalize these conditions here so that we don't get more men or more women or just more hostile, more, more dispositionally hostile people in one condition than the other. So, yeah. The thing is, just because we found a significant difference here, a statistically significant difference, does not mean that difference is important. All right, so just because we found a significant difference here, just because we're pretty damn confident that this difference is far away enough from zero to suggest a true difference, it doesn't mean that this is an important difference. All right, so in the next video, we're going to talk about practical significance or importance, which is a separate discussion from looking at the p-value and seeing whether we have a significant difference.